Let me check the audio settings first. Yep, audio settings are good. And then we're gonna do the share screen. Desktop 2. All right, so at least we got screen sharing done at this point. And we got a few people who are trying to join us online. So let me get to participants. We've got 1, 2, 3. Okay. All right. So I got everybody in, and it's time to get started with the rest of the lecture. All right. And I also have Logism already started. So this way I can get to the content a little bit faster, but I need to move that screen to the projection portion. Oh, one more person. All right. So this is just a register bank, which is not what you would actually need. How many people got a chance to read the document or the announcement that I sent earlier today? Two people, single digit, low single digit. All right. So you might want to read that, but in today's lab, there are also instructions on how to get to these files. So don't worry about, how do I get these files? How do I get it started? Because they're all included in the instructions of today's lab. So I do want to just kind of jump right in to the processor itself. This is the processor. This is the entire processor. There are 2 subcomponents that expands into their own circuits. We got one more person. There we go. So one of the subcomponents is the register bank, which is this thing here. That's called the register bank. And there's another component, which is the ALU, and this is the ALU up here. This is the register bank. And we'll go ahead and show the register bank itself. So this is what the register bank itself looks like. We have talked about every single component in this diagram or in this circuit already. So I hope you guys are feeling a little bit familiar with at least the components, okay? Maybe it's not how they interact and how they work together, but do we recognize every single component in this picture? Yeah. Are we good? Do okay? All right, excellent. All right, so what is the purpose of this whole thing as the register bank? It serves 3 purposes, okay? The first purpose is it houses the 4 software addressable or accessible registers. Those registers are called register A, B, C, and D, okay? So nothing too fancy here, okay? Yeah, they're just labeled A, B, C, D. And so that's the first purpose. The second purpose of the register bank is it allows a way for something outside to change the content of the 4 registers. Well, it can only change one of the 4 registers at a time, but if you adjust, okay, which register is being changed, you can change any one of the 4 registers. The third purpose, the last purpose, is up to there are 2 outputs coming out of the register bank. Each output can correspond to any one of the 4 registers. In other words, the 2 outputs from the register bank can correspond to 2 different registers inside the register bank. But if it is necessary, we can also use exactly the same register to connect to both outputs. Are we doing okay so far with all of those concepts? Maybe, okay? So we're going to get back to this, okay? So we'll talk about what we want to do, and then we'll look into how to get it done. And that's how we can find out how all of these things are going to work together. Are we good so far? So if I go back to my Joplin, which reminds me what I need to talk about. So you can see, the thing that I want to do today is I want register B to store the bitwise end between register B and register C. That's all I want to do. So if I go back to the circuit diagram, what I want to do is to take the content of register B, which is currently 0, 0, and I can zoom in a little bit because I think that makes it a little bit easy for you guys to see. So I'm going to use the content of register B and then do a bitwise AND with the content of register C, and then the result of that is going to be stored all the way back to register B. That's what I want to accomplish. So do we understand what I want to accomplish? Okay, so I can give you an example. Okay, so we'll go ahead and give register B a specific value. So this way we can talk about actual bit patterns. So with register B, I can make it CD in hexadecimal. So that means we have a bit pattern of 11001101 in register B. Now, do I expect you to be able to convert from hexadecimal into binary that quickly? The answer is no. Okay, it just comes with experience. Okay, but do I expect you to know how to do that conversion? The answer is yes. Okay, you can look up a table. You can understand, how the mapping occurs. But at this point, you need to know how to convert between hexadecimal and binary. Do we have any questions at this point? Okay, moving on. So register C, I'm going to give it some other value so that it actually would do something. In other words, after everything is done, register B will be changed. Okay, so with this one, I will turn it into 8. Okay, I'm thinking about what would be good here. 9 is good, but I think adding a 2 to that or 11 is even better. So 8B over here. All right, so before we do anything, can anyone tell me what would be the result of B gets B and C? And when I say AND, it is a bitwise AND and not a logical AND. So what would that be? And how would you figure that out? Okay, so we got CD and AB. Let me go back to Joplin. So this way I can show you how to do the calculation. So in this case, B has a value that is CD. DC has a value of 8B. So the first thing we need to do is to convert these into binary because it's pretty hard to do it, in hexadecimal digits. But once you see the binary bit pattern, it'll be a whole lot easier. So in binary, CD is 11001101 in base 2, and then 8B is 10001011 in base 2. So the bitwise AND of both of these would become B should be updated to. So the most significant one here is and 1 is a 1, and then 1 and 0 is a 0, 0 and 0 is a 0, 0 and 0 is a 0, 1 and 1 is a 1, 1 and 0 is a 0, 0 and 1 is a 0, 1 and 1 is a 1. All right. So this is supposed to be the result. So the result in hexadecimal should be 8, 9 instead of 8B. Are we still doing okay so far with this part here? With the operation of bitwise AND. Bitwise AND simply means, bit 0 of the first operand is ANDed with bit 0 of the second operand. Bit 1 of the first operand is ANDed with bit 1 of the second operand, and so on. That's all it does. Now, I think we should know this already because we have used multi-bit gates already. This is how we got G in the carry look ahead adder. And of course, some people are thinking, what carry look ahead again? What G are we talking about? G is the term that we need to compute the T's, the borrow bits in a subtractor, but also the carry bits in an adder. Are we still doing okay so far? Are we relating these concepts? Because the important part is to relate the concepts. So this way you have multiple pathways in your mind to connect all the concepts. It becomes easier for you to understand additional concepts. Are we good? Yep. Huh? Zoom in a little bit. I think I can. So let's give it a try. Yep, you can zoom in using Control+, which is a typical thing to do. And I can get rid of the other two windows, which are not needed. There we go. All right. All right, so with that, Okay, now that we know what we're supposed to do, the next question is, how do we do it? In other words, we go back to logic sim and then we ask the question of, all right, so this is where we can store the data to be processed, okay? And this is also where we can store the result after the computation, which is just a bitwise AND in this case. So in other words, registers they're useful, they're really, really useful because they are providing the most basic way of storing something that can be utilized for computation. They can also store the result of computation. But you only have 4 of these things, okay? So that means you don't really have a whole lot, okay? You really need to use the memory, to store variables and whatnot in general. But right now, we're not concerned about memory. We are only concerned about, in this specific case, how do we perform the bitwise AND and store the result back to here? So now the question is, where's my AND? Where's my multi-bit AND gate? I showed you guys that on Tuesday, kind of toward the end. Yeah, go ahead. In the ALU, exactly. So the ALU is called the arithmetic and logic unit. So that's where it is. This is the ALU. So when you view the ALU, can someone identify the one component that can perform the bitwise AND in this picture? You can just kind of describe the shape of the thing. So there are 2 things that has a round nature to it. One has a straight end, one has a curved end. Which one would it be? Straight end, yeah, exactly. So this is our AND gate here, okay? So the question is, how do we get the content of register B to get to one of these 2 inputs of this AND gate? It's a multi-bit AND gate. And get register C to get to the other input of this AND gate. And when it's done, how do we get the output of this AND gate all the way back into the register bank so that register B, this thing here, is going to be updated based on the result of the bitwise AND? That is the question. Okay, so let me ask, do we have any questions about what I want to accomplish? No questions? Okay, so what would you do? I mean, if this is a puzzle, it is presented to you, and I ask, okay, give me a way, give me a path so that I can connect register B, register C to the AND gate, and then we store the result of the AND all the way back to register B. So what would you do? What would be a good starting point? Yes.
So with the multiplexer to BNC and then just connect it like that.
We have a bunch of multiplexers and demultiplexers, but remember what they serve. Okay, what is the purpose? What are the purposes of multiplexers and demultiplexers?
They're switching.
Just switching, exactly. All they're switching. Okay. The only difference between the multiplexer and the demultiplexer is, do we have multiple input and we select one of those to connect to the output? Or is it the other way around, where we have one input and we have multiple outputs and we're selecting where the input is supposed to connect, which output should connect to the input? So that's the only difference between a multiplexer and a demultiplexer. But in terms of at a higher level, what they do, they are really just switches. They help to route components, they establish routes between components. That's all they do. Okay, yep.
Real quick, can you go over what the decoder was again? I know it was fairly simple, but isn't it like a multiplexer?
Say that one more time.
The decoder on the left.
The decoder. So a decoder is basically a demultiplexer where the input is a constant 1 bit. It's a constant bit of 1, I should say. So it has one single input bit and it's a constant of 1. So all you're trying to do is to say, where should I send that 1 to out of the 4 outputs?
So right here, is it being used as a clock bit?
No, it is used to decode. I mean, that's exactly what the decode is supposed to do. Because register input select, which is connected to the select port of the decoder, will determine which one of the 4 outputs of the decoder should become a 1 when the decoder is enabled. So that 1 will go into the enable of the corresponding register, which allows that register to update on the next rising edge of the clock. So that's why it's really important, because that is how we say, okay, out of the 4 registers, you are the one who should update. Even though every single one gets the same data at the D port, only one has the enable being a 1 at a time. All right, good questions. So what we'll do now is, I mean, you can start from this part. You can also start from the other part. I'm going to start with the ALU. So from the ALU's perspective, I know that we have to route, I'll get to you in just a moment. So we know that we have to route register B to one of these 2 inputs. We have to route register C to one of these 2 inputs. We also need to route the output back to register B. Okay, so we know that already. Let me address your question. Go ahead.
Is this a updated or version processor? The one I was announcing such different in the ALU.
They should be about the same. It's only the bottom has is shifted up a little bit.
Mine was the same. Mine has 7 outputs. It's almost the same
They
except for 7. Are you in the ALU or the processor?
Isn't the ALU?
Like cheaper.
Yours is indeed different. That is.
I'll look to see if I downloaded tricks.
No. It's fine. It doesn't change what we're doing here. So I wouldn't, worry too much about it. I think yours is a work in progress. I was intending to add 2 more opcodes to it, so I can do hardware multiply, and that's why I see a multiplier there. So you must have downloaded it fresh from the share drive. This is has been sitting on my drive locally for a while. So this is the older version of what I have been using in my classes. So don't worry about it, because it still works the same way as far as what we are trying to do here. All right, so here's the question. How do we route this wire? Okay, let me use the poke tool here so we can focus on the node. How do we connect this node all the way back to here? That's the question. Do you guys remember when you were younger, you would have these maze puzzles that you have to solve, like here's the mouse and here's a piece of cheese, and then you have to kind of find a way to connect the 2. That's what we are doing here. Except at every single junction, we have to also decide, well, in order to make a right turn, what do we need to specify? What do we need to use to specify the select of this multiplexer or this demultiplexer and so on? But other than that, other than that tedious part, that's all we're doing. We're just making a path between the components. Okay, so this is coming in from reg in. So if you go back to main, reg in corresponds to this wire here. So now the question is, how do we get, okay, so let's go back to the outside first, get back to the inside. So we are trying to make this wire connect to what we mentioned earlier, which is the D port of register B. So the first thing is to get it out of the multiplexer. In other words, I need to connect this to this node over here. Can somebody tell me what I need to do?
Change the op selector to the corresponding.
Exactly. Yep. Okay, so op cell or operation select, this thing here, this input pin is connected to the select of this multiplexer. And we have to count from 0. So remember, we have to count from 0. So that means we have 0, 1, 2, 3, 4. So this will be operation 4 in decimal. But when you specify the operation, you can see it is in binary. So the question is, what do we need to do here so that the output of the AND gate becomes the output of the demultiplexer? What is the bit pattern? 100. Okay, very good. So now we have solved the first of many steps. Okay, but the rest of this really is about the same. Okay, it does get tedious and boring at some point. Okay, So now that we know how to get the output all the way to here, now we have to look at this particular output pin and find out, okay, what does that look like from the outside of the ALU? So there are several ways to do this, okay? So you can look at here, and then you can look at circuit appearance. So this out here, nope, that's the register bank. We are looking at the ALU, sorry about that. So when we look at the appearance of the ALU, all you need to do is to click on one of the output, and you can see that, I mean, you guys cannot really see it, but in the picture at the lower right-hand corner, it also highlights the corresponding pin. This is the one that we want, okay? So out coming from ALU is where the output of the AND gate will connect to as long as operation select, which is simply known as select here, is 1, 0, 0. So let me just pause and make sure that you guys are all, making all these connections at this point.
This inside the bigger one.
This is the component, this is the appearance of the ALU. So we want to identify which pin from the outside view of the ALU is corresponding to the output that is coming out of the multiplexer, the demultiplexer, I should say, sorry. Are we doing okay so far? Okay, so even if you cannot follow all the details, okay, you have to kind of understand the general idea of how we track things down, okay, that's important. Okay, so now we can go back to the main circuit, and we can now identify, okay, so we have to go back to the poke tool here. So now we know, after the AND operation is done, this node is going to have the result of the AND. Are we still doing okay so far? How I can identify that particular node or connection to have the result of the AND. We good? Okay. So now the question is, where do I need to connect this to in terms of the register bank? So now we right click on the register bank, or I can just take a look at the register bank here. So what we want is register B to be updated. So we are looking at this particular wire, and that connects to this pin here. So even though in the circuit, you know which pin it connects to, from the packaging perspective, from the appearance perspective, sometimes it's not one-to-one. If I make a mistake and then fix it later, then the relative positioning of the pin in the appearance may not correspond to the actual location inside the circuit. Some of you actually did that in your 3x3 adder, and I kind of help you spot it, that problem. So that means, to be sure, I need to look at the appearance of the register bank and click on this thing here, which I suspect is corresponding to the pin that I was looking at. And in the picture, it does show me that it is corresponding to the input pin that I've been looking into. So that's important because I don't want to make an assumption of the relative position of a pin in the appearance of a chip corresponds to the actual pin inside the circuit itself. But now that I'm certain, I can now go back to main and go like, okay, so we need this wire. Nope, not that wire. We need this wire to connect to this wire over here. In other words, we want to have this thing to connect to here. So let me pause again and make sure that we understand why we need that connection. So do we have any questions about why we need that connection? Nope, we're all good there, okay? So how do we make that happen? By the way, what is the name of this thing here? The one thing that is separating the two connections that I need to hook up together. It's a multiplexer because it's a mux, okay? So what do I need to do to this mux to make that connection happen? This mux has 2 inputs, 1 output, but then it also has 2 more ports, at the bottom of the multiplexer. Yep.
The block needs to update and the selector needs to be on.
We need enable first, right? So RIEN needs to be a 1 first. It is a dark green right now, so it's a 0, but we want it to be a 1. right? Because we need to enable the switch. This is one of the switches where it can be disabled. So before we want the switch to work, we have to enable it first.
So it doesn't work like this.
Yeah, this one, yeah, multiplexers and demultiplexers do not care about clocks. Yeah, because if they don't update, they're basically pass-through devices. So once you make the switch, when almost whenever the input changes, the output will also change at the same time. It does not have an edge to update any. Yep, go ahead.
No, I saw that.
Oh,
I figured it out.
oh, okay, excellent. All right, so we need the RIEN to be a 1. What about this thing here that is under a gray dot? What is the significance of that gray dot? We talked about this when we talked about multiplexers and demultiplexers. Yes. It's the select pin. Go ahead. It's the selector. So in this case, how do we want to configure the selector when we want, okay, let me highlight which input we want to connect to the output. We want this input to connect to the output. So what do you think RI mux should be? It should be a 1 because we are connecting input 1 to the output. Okay, because if the selector is a 0, it connects input 0 to the output. When the selector is a 1, it connects input 1 to the output. So you are correct. Okay, we want RI mux to be a 1. We want RIEN to be a 1 as well. Very good. So now that we know how to get that signal all the way back here, the question now is, well, this input pin connects to all 4 registers. A, B, C, D, they all have their D port multi-drop connected to register input. So the question now is, what am I going to do to say, register B, you are the only one that should update? How should we do that? Yep, reg in select, okay, register input select. So this pin here is connected to, guess what? The thing under the gray dot again, which means it is a select. In other words, it is selecting one of the 4 outputs of the decoder and see which one should become a 1. Well, first of all, we need the decoder to be enabled, but this is our registered input enabled. So it's already connected outside. So assuming the decoder is enabled, it has a 1. How should I configure reg in select in order for register B to be the only one that is enabled to be updated in the next rising edge? It should be 0, 1. Very good. Now, how do we know it should be 0, 1? Because this is output 0, this is output 1, this is output 2, this is output 3. But we are looking at 0, 1, 2, 3 as decimal numbers, but we need to specify the select as a binary number. 1 in 2 bits is 0, 1. So we know that register in select or register input select should be 0, 1 in order for that to happen. So are we doing okay so far with this? Now, this is not done yet because we have just found the route going from the output of the AND gate, going back to the input of register B, so that register B would be updated by the end of the operation. But what we have not figured out is how do we get the current content of register B and register C to the AND gate to begin with. So we will do another trace. Okay, so this is just a trace. So this time we start with the ALU again, and this time we start with the inputs. Okay, so this is one of the inputs. So we want this wire to be connected to this wire here because this is one pin that can bring in some data. So the first question is, what should I use? What do I do to make that connection? This node should connect to this node over here. What controls that? It looks like this thing here that is sitting in between is what we need to configure. Does that make sense? So first of all, it needs to be enabled. Okay, that's easy because it has an enable pin that is currently dark green. And that one goes everywhere. It goes to ALUEN, which stands for ALU enable. Okay, kind of makes sense that you want to enable the ALU when you want to perform some operation with the ALU. So that part is easy. Second question, how do we make sure that the input from in1 as a pin connects to the wire that is highlighted at this point? The select, and what should be the value of the select? In other words, if you look at the gray dot underneath, that wire goes to the same OPSEL or operation select. We figured that out already. 100. Okay. All right. So now we got that routing done. We might as well talk about the other input since we are here already. So the other input of the AND gate is this particular node. And you can see it connects to the output of another demultiplexer right here. And this particular demultiplexer is supposed to connect to this input pin here. And in order to make that connection, guess what? It is also controlled by OPSEL. It also, the 100 of operation select will configure both of these demultiplexer as well as the multiplexer as an output. They all work synchronously in order to divert the input to the correct operation and then direct the output of the operation to the output. Is that okay? All right. Okay, so that means our focus should now be looking at in1, in2 of the ALU. So when you look at it from the main circuit perspective, we are looking at in1 and also in2 like this. So we'll work with one at a time, okay? We'll work with one of them at a time. So let's talk about in1 first, okay? So we need in1 to connect to one of the output of the register bank. So we need this wire to connect to this wire here. The question is, how do we make that connection? They are separated by a demultiplexer, very good. So this is the demultiplexer that's separating the two nodes that we need to connect. So now the question is, how should we configure that demultiplexer to make that connection? What do you think? Well, first of all, we need to turn it on. Turn it on, right? So we need RO0EN, register output 0 enable, to be a 1. And then what else do we need? The gray dot. The gray dot needs to be what? 0, 1. It needs to be 0, 1 because this is output 1 in base 2 using only 2 digits. It is known as 0, 1 in base 2. Okay. And what about the other input of the ALU? So the other input of the ALU is connected a little bit weirdly. Okay, there's a reason why it's weird. But the first thing it goes to is a multiplexer. So in other words, we have 2 inputs, and this is the output. In this case, the select, which is FC, connects to FC, is not even something that you can directly control, because when you track down FC as a total, it goes all the way up to here. And as long as one of these two is a 0, the output is going to be a 1 for FC. But what do we want in this case? We want this output to eventually connect to this thing here. So that means the first thing is for it to go past this demultiplexer. So how do we connect this node to this node over here? This one does not have an enable, it only has a select. So all I need to know is what is the select supposed to be? What is RO1 debug supposed to be to make that connection? Should be a 1. Very good. Okay, so now that we know how to get out 1 from the register bank through the demultiplexer into this multiplexer here, how do we get this wire or this node to the output of the same multiplexer? This is input. It's input 0. Very good. So we want FC to be a 0, not a 1. So now the question is, how do we make FC as a total of a 0 instead of a 1? FC is defined all the way up there. It is the output of a NAND gate. So how do we get FC to become a 0? Most of the inputs need to be 1s. Very good. So we need register output 1 debugs to be a 1, which coincidentally is also what we need to route this thing to here. Okay, so that's done already. And then the other thing that also needs to be a 1 is ALUEN, which is also going to be a 1 because we are going to perform something in the ALU. Are we doing okay so far? Right? So now we know how to connect the output of the register bank to the input of the ALU so that we have a connection between those two components. The last portion, okay, is to go into the register bank here and ask, well, how do we get register B to the output 0? And how do we get register C to output 1? That's one of the two ways to do it, but we'll just kind of focus on this one. What do you think? What do we need to configure so that port Q of register B connects to register output 0? The selected of this particular multiplexer, and what should it be? 0, 1. Very good. So 0, 1 specifies register B. Okay. And then next question is, how do we connect port Q of register C to register output 1? 1, 0 for register output 1 select. That's it. You guys have just figured out all of that stuff. Okay, lots of 0s and 1s, right? Are we doing okay so far? Are you guys feeling a little bit better now? Or not? Okay, that's a silence, right? Good thing this is all being recorded. All right. So now this is how it happens, okay? This is what a microcode slice needs to do, is look at all those things, okay? RISEL. Who comes up with RISEL? This is the consumer of that tunnel. But where is it coming from? RISEL is right here. It connects to the output of ROM. Okay, what about the other things that we talked about? Register output 1 select. Where is it coming out of? Register output 1 select is also coming out of the ROM. So the data port of ROM is giving us all these control signals so that we can tell this switch, okay, for this switch, I need you to turn this way. For this switch, I need you to turn that way. This register, I want you to enable. That register, I want you to turn off, and so on. So that's how things happen inside the processor. Okay, you have all of these control signals or control bits. RIEN is a control bit, RIMux is a control bit, PCEN is a control bit, and so on. But most of those, not all, most of those are coming out directly from the ROM's output. If I were to scroll this picture down a little bit, you would see that all of those, okay, these are coming from a splitter. That splitter is called UCode data, and UCode data itself is one of the split end of this splitter itself. So they all eventually come from the ROM. So the ROM is actually dictating how connections are made between the components. Once the components are connected, then the clock comes along and say, do it. Okay, every time we have a rising edge, it is basically saying, do it. Register, update, okay, but only for registers that are enabled. So the registers that are not enabled, they're just going like, I'm not going to do a single thing. Is that okay so far? All right. So if for every little thing that you have to do, you have to figure out all of these bits, it will take you eons to write a program. Okay, so that's why there are opcodes. Okay, what you store inside the ROM, each location is what I call a slice of microcode. as the name implies, microcode is a subcomponent of quote unquote just code. Okay? What you need to specify in the end as a programmer is opcode. Okay, and opcode do not reside in ROM, they are going to be specified in RAM. So the question is, what opcode in RAM is going to do what? So this is where the opcode table is going to come in handy. So let me switch to the opcode table. Okay, where is that? This is the opcode table. So the link to the opcode table is in today's announcement, but it's also in the lab instruction for today's lab as well. So don't worry, you will get a link to this document here. It's also in the shared folder. So for those of you who are curious and you have just been poking around, you would have found it also just by accident. So this is it, okay? This table describes everything that the processor TTP can perform. And we have how many instructions? We have 7 to 33. So 33 minus 7 is 24 plus 1. So we have 25 instructions. There are only 25 instructions in this particular process. So do you think this is going to classify as a CISP processor, or do you think this is going to classify as a RISC processor? CISP stands for Complex Instruction Set Computer. RISC, on the other hand, stands for Reduced Instruction Set Computer. So do you think 25 instructions is considered complex, or do you think it is considered reduced? It is way reduced. So this is W of RISC, way reduced in computer. But it's not a purist, okay? It could have been even smaller. There are certain instructions I have to put in here because otherwise the program is going to be so tedious. Yes?
What's like the biggest?
In terms of CISC?
Yeah.
I do not know, but I think that would probably be the processor in an IBM mainframe computer, because those things have a huge number of instructions. The Intel processor also has a really large number of instructions. I think they're at least in, they're probably in at least 1,000. Yep. So in a way, RISC is nice because it's easier for you to choose which one you need to use because there are only 25 to choose from instead of 1,000 to choose from. Okay. In another way, it's kind of nasty because each instruction only does this much instead of this much. So it's a trade-off, okay? The trade-off is there, there's a balance, okay? Obviously, there's a balance to everything, but currently the balance is, the mainframe or if you want massive computation power, the balance is shifting or leaning to the RISC side because they are more energy efficient. So even though each instruction doesn't do as much, it doesn't take nearly as much energy to get the same thing done compared to a complex instruction set computer. Yes?
You repeat what CISC stands for?
CISC stands for Complex Instruction Set Computer. And then RISC, the R stands for reduced. All right. Well, looking at this thing here, can someone, let me zoom in a little bit so that you guys can see a little better. Can someone tell me which row seems to suggest, that's what we need. So do you see something here that is telling you that's exactly what we were trying to do? Row 28, very good. Okay, so we are looking at row 28 here. And let me zoom in a little bit more because this time we have to look into the specifics of row 24. Row 28, that's it. Thank you. So row 28 has a few columns, meaning there are columns for every single row. Column A is a bit pattern. Okay, column A is giving you a bit pattern of what opcode you need to store in RAM to perform this operation. Is that okay? So some of these have definite zeros and ones throughout, not on this particular page. But some of these have 1100, so those are verbatim. 1100 must be where they're supposed to be. But then we also have XXYY. XX together, these two bits specifies register X. Now, you guys are going like, but you just said there's only 4 registers, registers A, B, C, and D. Yes. So XX is a placeholder to basically allow you to specify which of the 4 registers you want to be register X, and then YY allows you to specify which of the 4 registers you want to be register Y. Okay. So the column A is the opcode. Column B is what we call the mnemonic. So we'll talk about mnemonic in just a little bit. Okay. We'll skip to column C. Column C is basically quote unquote C code, but it is actually what I call RTL. Okay, it's an RTL description of the operation. RTL stands for Register Transfer Language. Okay, in other words, it's trying to specify, it's trying to tell you what is happening in the processor using registers as the main concept of as the quote unquote variables involved in the calculations. So in this case, if X specifies a register, Y specifies a register, then the operation can be seen as this assignment operation, where X is updated by the bitwise AND between X and Y. Are we doing okay so far with this? All right. And then the last column, column D, is nothing more than just an English description of what the opcode does. So what about column B? Okay, we skipped column B. It is called the mnemonic. And by the way, there's a movie called Johnny Mnemonic. Great movie starring Keanu Reeves. Okay, it's a great movie. It's an interesting sci-fi movie. Okay, I have to tell you that much. Yeah, watch it and tell me what you think of it. Okay, after the semester ends. Anyhow, so the question is, if every single time you want to perform a bitwise AND, you have to look at this table, you have to find out which 2 registers are supposed to be ANDed, then you have to figure out the bit pattern of how to specify register A, register B, and so on for X and Y. That's going to take a long time. That process is called assembly. Okay, you're trying to figure out from what we want to do and come up with the actual opcode, which is 8 zeros and 1s. Okay, it's tedious. Can you do it? Yes. Do you want to do it like hundreds of times? Probably no. What about thousands of times? Probably way no, right? Okay, so that's why we have mnemonic. Column B is mnemonic. Mnemonic is basically a way for you to specify the opcode, but in a way that is slightly more user-friendly or human-friendly. I mean, some of these you can see that it's not exactly spelling out everything. Okay, for instance, we have CMP_XY. It is compare XY. Okay, we're not spelling out compare. Okay, CMP is what we use. So the mnemonic is a little bit abbreviated because I don't think you want to type a lot of characters either. But that's what you can. That's how you can specify an opcode using the mnemonic, and then a tool is going to help you convert from the mnemonic to the actual opcode. That tool is the assembler. So this class still has the name of assembly language programming, and that's what assembly language is. Okay, it is basically converting mnemonic representation into opcode or binary representation. Are we doing okay so far with everything that I have talked about so far? Okay, it's 6:24. We'll go ahead and take a short break, take roll, and then we'll continue with this. Yes.
So for bitwise AND, we have 1100 and then 2 X's and 2 1s.
Right.
The 2 X's get replaced with bit pattern.
Yes.
One register.
Indeed. So let me finish this part before taking roll, because this is a relevant question. So the opcode table has these 2 rows at the top that basically gives you exactly what you need so that you know what is supposed to go to XX, what is supposed to go to YY. Because there are 4 registers, so 2 bits will be enough to differentiate any one of the 4 registers. So each register becomes a 2-bit pattern. 00 is specified register A, and then 11 specifies register B, and so on. So with that knowledge, okay, if I go back to the AND instruction on row 828. So if this is what we want to do, okay, because what we want to do is B gets B and C, right? That's what we wanted to do in the first place. So register B is known as, is identified by bit pattern 01. So that means XX becomes 01. YY is trying to specify register C, which is represented by 10. So that means the actual opcode for and BC is going to be 1100 0110. So that's what this XXYY are for. They are placeholders so that you can use those placeholders to specify exactly which register you want to be X and which register you want to be Y. Very good question. All right, so with that said, I am going to switch back to Canvas. Oh, Canvas is in the browser already. And we'll go ahead and take roll. I did not make a QR code today, so let me make it visible. Oh, actually, give me a second here. I'll make it visible first, and then I'll show you the passcode. So if you refresh, you should be able to get into the activity now. And then the access code is, okay, let me give it a due date first. We'll make it 6:50 p.m. That should be plenty of time. And in the next page, I don't really like the new interface, but that's how they want to do it now. So the access code is TTP-ASM, which stands for Text Toy Processor Assembly. Yeah, today is important, and so that's why I really want to make sure that people are here today, or at least in their life at least. Because today is the pivot point between the components, all the logic gates and whatnot, and we are pivoting into the processor. We are starting to understand how to write code starting from today. Yep, TTP-ASM, you will hear that quite a few times from here on. Text Toy Processor Assembly. All right, so can I switch the screen back to the discussion? Does anyone still need to look at the this screen here? Nope. Okay. I'm also checking the online people. Nobody seems to indicate they need to look at this. All right. So the next thing is to showcase the assembler. So this is the assembler. There's also a link. Don't worry. There's a link to the assembler in the lab instructions. So don't worry about this. So with the assembler, the first thing you need to do when you do your lab, the instructions are included anyway, but I want to show you how to do it, is to go to File and then go to Make a Copy like this. And most people just click Make a Copy. Don't do that, okay? Because if you try to do this, it will try to make a copy in my folder, which is not going to work. So what you need to do is to make sure that you click on Folder and make sure that this goes all the way back to your drive, and then you can create some folders and whatnot if you want to, okay? But do not just pick the default folder and then click Make a Copy, because that will not work. The second thing is, I will say this several times, but I think every semester at least one person will do that. Do not download this and expect it to work in Excel. It will not. Guaranteed, 100%. Okay, so this will only work as a Google Sheet. So now we go to the source tab. There are many tabs in this particular spreadsheet or Google Sheets. So go to the source one, okay, because this is where you put in your code. And then you can type your code in column A. You can also copy and paste from a text editor. Any text editor will do. Notepad is going to work. I'm not really sure what is the equivalence of Notepad in Mac OS. Does anyone know?
I think it's Notepad.
Is it Notepad?
Text edit.
Text edit. Okay, so text edit probably will work too. The thing is, if you're copy and pasting, make sure it is not in a blinky cursor mode when you paste. Okay, that will not work. If you're copy and pasting, you want to paste when it does not have the blinky cursor. Anyway, so I'm gonna just type in the code and BC, okay, because that is the mnemonic of the opcode that we were trying to figure out earlier. Are we doing okay so far with this? Okay, and then we can press the enter key, okay, because right now it is not entered yet. And I can zoom in a little bit so you guys can see the detail a little bit more. Usually I change the resolution of the projector to get around this problem, but this particular projector does not like the resolution that I want. Okay, so now it's done. We do not see anything in column B because if there are errors, they'll be reflected in column B. Okay, so this one assembles just fine. And then we can explore some of the other tabs. Now you can see some of these tabs have a lock on it. It means, if you mess around with these particular tabs, you can break the assembler. In which case, you just have to make another copy from the original, okay? So if you go to the assemble tab, it would actually tell you what code it assembles to. Do you see the column C, column X? It has C6 in it. So C6 is what? 11000110. Do you remember that big pattern? That's what we figured out earlier, right? So the assembler can take the mnemonic and convert it into opcode for you. So that saves you a lot of trouble. Okay? But does it mean that you can only rely on the assembler, for exam 2? The answer is no. Okay, you will be asked to assemble opcode given what it is supposed to do. Just so that I know that you know how to do it. Okay? It shouldn't be too hard. Okay, once you figure it out, it's not really that hard. All right, so the next thing, let me look at how much time we got. It's only 32. We got plenty of time because I want to show you how to get this opcode into RAM and then actually run the program. Okay, because I want to finish the whole thing, is to illustrate how it actually executes. So to run the program, you can just copy C6 into the first location of RAM. That works. The other thing I would also demonstrate is you typically want the program to end with a halt instruction, because if you don't end the program with a halt instruction, it will keep going, which is not what you want. So a halt instruction has an opcode of 0, 1. It is not really important at this point, how the halt instruction itself works. We'll just put it here. The tab called RAM file is really important because this is where you can download a file and then you can load it into the RAM component of TTP directly. So when the program is short like this, yeah, you can just type it into the RAM component by hand. It's not a big deal. On the other hand, if the program gets a little longer, I think this is going to be a really good shortcut. So to use this particular shortcut, you go to File. When you are in this tab, in RAM File tab, you click File, and then you go to Download, and then you specify one of these two, CSV or TSV. They will both work. But personally, I'm going to use CSV, and I will use it consistently. Depending on your browser, okay, mine is configured to ask me where to save that file and what name I want to save it in. I would recommend you to do the same thing, but you don't have to, okay? Because I don't like spaces within the name of the file. So I'm just going to call this one test.csv, click save, and now the file is saved. So what I can do now is to switch back into Logisim. Okay, so let's go back to Logisim, go to the RAM component. Okay, so get to the RAM component, and then you can right click, go to load image, and then go to the folder where you saved that file. In this case, my file is saved in the temp folder. It is called test.csv, and then click open, and you can see the content of RAM is now updated. So now we have the program loaded into RAM and it's ready to run. Are we okay so far with all these steps? Okay, the lab includes all the instructions. Okay, I'm just doing it in class one so that you guys can see visually what you should be seeing. Yes. Nope, this is all coming from the file. Yep. All right. So now we are ready to run the program. So how do we run the program? How does this whole thing work? I mean, look at all of these crazy connections, right? I mean, it's like, where do we start? So this is where the new module is coming in handy. Let me point out where it is so that you guys know at least where to find it. I wrote it just today because I just thought, hey, most people probably need to have a little roadmap of how to get to understand the processor. So this is the module that I wrote today, module 0383. It is also in Canvas already. So if you go back to Canvas, you should be able to see it. Let me get back to the Canvas module and then point to the module right here. So this link here is the same as module 0383, and the title is TTP explained in parentheses, sort of, because I still want you guys to do a lot of the investigation of how things work. I'm just giving you pointers of where to start, how to proceed, the general strategy, but eventually it is still up to you to have to kind of go through that investigation process at least a few times to get a really good feel of how it works, okay? All right, but I'm gonna do it by hand today, okay? So I'm gonna do a little demonstration today. All right, so everything starts down here. This is the conductor. This is Sir Topham Hatt. This is the component where everything starts. So when the ROM is at location 00, this is microcode pointer, it's not Ucode, because mu, which stands for micro in Unix, sometimes it's written as U, because we can't really type in mu on the regular keyboard. So that's why Ucode pointer is actually microcode pointer, because it points to a particular size of microcode. So when microcode pointer is 000, because everything resets to 0, including the microcode pointer, it has a certain output here. So we want to look into this particular output from location 000 and find out what exactly does it do. Okay. So you look at this and go like, oh, this is going to be a headache, right? Because how many bits are we talking about? We're talking about 1, 2, 3, 4, 5, 6 hexadecimal digits. 6 times 4 is 24. There are 2 bits only with the most significant digits. So we are talking about 26 bits here. 26 zeros and ones, kind of like sprinkled over the entire processor. Where do I start to understand what is going on here? Well, fortunately, there are only a few main components that are called active components. So let me identify the 4 or the 5 active components. It is also in the module itself. So that is also helpful. One is the register bank. So the register bank, you know whether it's active or not when you look at input enable. Is it enabled? If it's not enabled, then you're not updating any one of the 4 registers. You look at register output 0 enable. If it's a 0, it means we are not using register output 0. And there are no instructions that would make use of output register 1 without using output register 0. Okay. So that's one active component. Another active component is the PC or the program counter, which is down here. So I would suggest you to print a picture like this and use a highlighter to highlight the main active component, the register bank, the program counter. The job of the program counter is to identify where in RAM, what is the address in RAM, can I find the next opcode. That is the job of the program counter or PC. If you're familiar with the Intel architecture, it is known as the IP or instruction pointer. Now, if you have never been exposed to the Intel architecture, just call this PC, the program counter. There's another register here called the instruction register. The instruction register is basically a temporary place for me to store an opcode that I'm reading from RAM before I can actually make use of it. Okay, so it's called the instruction register. There is the flags register. Okay, the flags register is not going to be useful today. We'll get to use the flags register when we are ready to talk about conditional jumps or conditional branch instruction. That's the only way you can have a form or basically a branch in assembly language program. But we're not going to, it's not going to be needed for today's lecture. And then there's one more. So the last component is the RAM component, which is all the way out here. So the RAM component is easy to identify whether it's being in use or not, right? Because it has a chip select. In this case, location 000 of the ROM is indicating that, yep, we need to use RAM because guess what? It is selected, okay? So once RAM is selected, it automatically prompts two questions. One, which location am I reading? Which location are we accessing? Two, are we reading or writing? And three, so I just like, there are three questions that we need to ask. The third question is, if we are reading, who is asking? If we are writing, who is providing the content? Does that make sense? That you should have three automatic questions as soon as you know RAM is being used. Okay, so we'll address those questions one by one. First question, which location am I reading from and who is telling me where I should be reading from or which location I should be accessing? That is controlled by port A of RAM. So what you need to do now, okay, I'm just finding my mouse pointer. There we go. So we need to now track down port A and say, okay, who is specifying, port A of RAM? Well, it's the output of this multiplexer here. So what do? How can we track all the way upstream to the thing that is actually providing the address so that we know which location we are interested in? Track the selector. The selector is likely, it is a 1. So which input of this multiplexer should I track down? The bottom one, very good. So we track this one down and it goes to the program counter. Now it does go to the adder over here, but this is not the output of the adder. This is the input of the adder, which cannot specify content. It does go to the Q port of the program counter. So that means the program counter is directly telling RAM which location we want to access. Is that okay? So that answers one question. Second question, are we reading or are we writing? Because this is RAM, you can specify one or the other operation. So we go back to RAM and we ask, how do we know whether we are reading or writing to RAM? This is a question, this we talked about on Tuesday. The LD, the load, right? The LD port. And the LD port is light green, which means it is a 1. So are we reading or are we writing? If load is 1, we are reading. Okay, so we are reading, which means the data port D is outputting the content at location 0. So it's outputting C6. Okay, we can confirm that. Okay, we can just kind of probe the D port here and confirm that it is C6. It is indeed C6 because we can see in binary, it is 1100, which is a C, 0110, and that is our 6. Okay, so then the question is, so who is interested in this C6 here? Okay, so now we have to go through the exercise of going through the remaining things and see which one is active. So we'll go ahead and just do it exhaustively. The first thing is, well, it goes to this demultiplexer or one of the outputs of the demultiplexer. That's a non-issue, okay? Because the output of the demultiplexer is an output, and this demultiplexer is turned off. Okay, we can see that register output 0 EN is a dark green, so that means that connection, this connection here is not of any concern to me. Let's check out some of the other stuff. Okay, so we'll look at this AND here. It goes to this input pin, and the RI mux is a dark green. But guess what? This multiplexer is not enabled because RIEN is dark green. It is not enabled. So this connection here is of no concern to me either. It goes to this multiplexer. Okay, this multiplexer has a dark green as a select, which means it's if it is used, it's selecting from input 0. So we have a dead end here as well. Are we doing okay so far of how I identify, is this useful? Is this useful? Is this applicable, and so on? Okay. So all of these are dead ends, except for this one here. Okay. So this is not a dead end because it is going into the D port of the instruction register, which means, okay, so if the register is enabled, it's going to update. Well, is it enabled? Is the instruction register enabled? Look at the EN. The EN is light green, which means it is a 1. So this instruction register is enabled, which means on the next rising edge of the clock, it will update. So that's how we can identify what we are about to do can be described as this. Let me go back to Joplin here. So what we are about to do is known as the fetch cycle, which is basically doing what this is describing here. Instruction register is getting whatever the program counter is pointing to. So if I were to use register transfer language, RTL, this is how I would describe what we are about to do. Is that okay so far? Okay. So let's go ahead and make that rising edge happen. So Control T gives me the rising edge, and now you can see how the instruction register becomes C6 because that is what we just read from RAM and put into the instruction register. All right. So the next time, the next operation is a falling edge. The falling edge would not affect any register except for the microcode pointer. This is the only register of the entire processor that updates on the falling edge. Everybody else would update on the rising edge. So the question is, how are we updating the microcode pointer? We know it's sensitive to a falling edge, and we are about to experience a falling edge. So you look at the input of the microcode pointer, it's coming out of a multiplexer. The multiplexer has 2 inputs. The select is saying, let's use input 1. Input 1 connects to the output of an adder. The adder is basically just adding 1 to whatever the microcode pointer already has. So what do you think is the output of the adder? It just increments by 1. So it increments to 0, 0, 1 on the falling edge. So I do want to finish this, because this way we actually get to finish one complete cycle of executing in single opcode. So that's kind of important. So now we move on to 001 in ROM, which means the output is now changed, right? So now we have to figure out what is this going to do. So I'm going to shortcut the whole thing. Instead of giving you the highway 1, scenic route, I'll give you highway 5 and just go straight down to wherever destination you need to go to. The program counter is going to update, right? Because you can see PCEN is a 1, so the program counter is going to update. So then you have to ask the question, how is it going to be updated? You track down the input, it's coming out of a multiplexer. The multiplexer has a select of 0, so we track down input 0. It's also coming from a similar structure, which is an auto increment mechanism. So we know the program counter is going to increase by 1 when we see the rising edge. Okay, so we'll do that. Control T like that. And the program counter is now auto incremented so that it's ready to fetch the next opcode. Okay, as soon as we fetch one opcode, we want to prepare for the next one. So that's why we auto increment the program counter. Now we have a falling edge. Falling edges only affect the microcode pointer. So we want to look at the microcode pointer and ask, how is it going to be updated now? This time you can see the select is a 0. So that means we are using input 0 to update the microcode pointer. Now, this is called the decode phase of instruction execution because this particular input uses the instruction register. Okay, the output of the instruction register goes to the total called instruction, but that only specifies bit 4 to 11. Bit 0 to bit 3 are constant of 0. So basically what we're doing is we are shifting the instruction byte by 4 bits to the left. So what we will end up storing in the microcode pointer is going to be C60 in hexadecimal. Because the output of the instruction register is C6 already, 4 bits is 1 hexadecimal digit. So that's why we're going to store C60 into the microcode pointer. So here's Control T. This place here, okay, you can see that this one is based on C6, which is the opcode that we are talking about. This slice of microcode is specific to AND BC. Okay, so we are running out of time, okay, but you can probably do this on your own, because what you can do is now go back up here, look at the register bank, and you ask, is register B ready to update? Is register B connected to output 0 of the register bank? Is register C connected to output 1 of the register bank? Then you go to the ALU, and then you ask, are we going to perform an AND operation? Is OPSEL 100? Okay, and I can assure you that's exactly how the processor is currently configured, because this is how we specify AND BC, or register C stores the bitwise AND between register B and register C. So that completes one instruction execution. We're running out of time, okay? That's one last thing where the microcode pointer has to reset to 0, 0, 0, so it's ready to fetch the next opcode, but that part is relatively easy to explain, and we don't really need that for today's lab. All right, so I do need to give you the access code of today's lab. There's only one, and let me get to it first. So today's lab is called familiarizing with the TTP tool chain. So it's more of a just kind of exercise. Put this here, put this over there. What is that? That sort of stuff. So let me give you the access code so that you guys can get started as soon as you get there. And there's no access code, or am I? Does it say no access code? Looks like there's no access code for this one. I just want to double check. Yep, there's no access code for this one. All right, so there's no access code. You guys can get started right away as soon as you get to the lab. It is due at 8:20.